Hello. Okay. I'd like to talk about free energy today. So I, in the context is not in physics and chemistry, but in the context I came across this in machine learning and so on in probability, and it bothers me quite a bit because the name like free energy. Then I decided to get into like chemistry and physics and trying to understand more like why they call it free energy. So anyway, like F is a expression, an expression, something like that. Like we're trying to, you see, like I first I will basically model something like different states. Like we have different states like given by X here, and we model the probability of those states with the Boltzman distribution as the follows. So basically, like you can think of each of the state have different energy, basically given by Ex here, and I try to be consistent to use script E here. Hopefully, I can remember that, like because I'm going to use expectations is going to overload the notation E here. So and as you see, like basically, if we have just a convention in physics and chemistry, when energy is higher, then the probability will be lower. So therefore, will be exponential minus the energy, and multiplied by the beta here. Beta is basically the inverse temperature. So beta is equal to 1 over T. So you can think of basically just an inverse temperature. And then and here, of course, this at the part in the bottom, at the bottom is basically just a normalization factor here. Typically, we call this use a notation z here. It's called the partition function. Um, and and of course, I can take a log of that. Then it's just called the log-partition function. So there's something like interesting for the log-partition function is that like it has actually sometimes I will denote it with a as well. So and yeah, it will be a function of beta here as you can see. So a beta um and yeah, c of course a function of beta as well. Uh this the log partition function have some interesting cumulant generating property. Basically, if you look at, for example, if I take the partial derivative of a with respect to, or maybe simply write log c with respect to beta. So what we get is we'll just have like take the integral here x e minus beta ex dx. Note that I'm taking derivative with respect to beta. So ex will come down. So I have minus ex coming down here. So then this expression is uh wait a sec, I'm sorry about that. I forgot like I have 1 over c as well, right? Because I taken derivative of log c. So I first have 1 over c, and then I take the derivative of z here, this just this one here. So then I have ex coming down. So I have this one minus ex coming down. I have this one, and then of course my c here can absorb into that. I will have like x minus ex, this e beta ex z dx here. This is just the probability, right? So this is just px here basically. So therefore, this is nothing, just the expectation of the energy. So actually, I should have a minus sign, minus the expectation of the energy. By the same token, you can try to do like partial derivative of log c with respect to beta, take second order derivative, like take the partial derivative twice. We'll basically get the variance of the energy, basically. So, so therefore, you can see that like this of course this variance will be bigger than equal to zero. So therefore, like this a function is actually, or this log c here is a converse function with respect to beta. Um, and okay, this is a for the partition function. And now back to our free energy here. So free energy, we have this form like this. So this is essentially just a partition function, right? This is actually just a partition function here. So one way we write that is like f is equal to -1 for beta log c here. So we can just exchange, do some, move the terms around. So we will have c is equal to exponential minus beta f, something like that. And sometimes in the literature, you can also see that we'll have something like the F is not the total free energy, but we are looking into the free energy for given some variables. And this partition functions is compute in the way that we're integrating all the latent variables. So for example, I may have like fxy is equal to 1 minus beta log cxy here. And this cxy is something like exponential minus beta e x y z dc. So basically like c is the latent variables. So we kind of like integrating over the latent variables, and for the remaining variables, we just keep it there. So then our free energy will be for that case will be the free energy for all the visible variables, the non-latent one. For different visible variables, we have a different free energy. So we'll come back to that. Don't worry about that. Like we'll come back to that at the very end. So and let's see what else I want to mention. And oh, okay, yes. By the way, like why we're calling this free energy basically. So that will get us back to physics and chemistry. But first thing we look at is like we want to look at the entropy. So what will the entropy looks like? So here I will just use the chemistry and the physics notation. I will use S instead of H here. Just because H in chemistry they have a different meaning like enthalpy or something like that. So I will use S as the entropy is just equal to minus the expectation. Oh, okay, maybe I should open. Should I erase something or create a new page? I'm thinking about. Yeah, maybe it's okay. Let me just use here. Maybe I have enough space here. So maybe just equal to minus log p x, right? And my minus log px here is equal to, my px is just equal to this guy here. My px is just equal to this guy here. Is equal to exponential minus beta ex over the partition function. So therefore it's equal to log of the numerator. So we have like expectation beta e x, right? And then I have minus, okay, I have minus, so it's plus log c there, right? So I'll just have that. Beta is a constant, I can pull it out, so I have beta expectation ex, right? So this one is just the FH energy, right? And we know what's the expectation ex. It's just equal to the partial derivative of log c over beta. But let's keep it like let's keep it like this for the moment. And plus log c here basically. Now, and let's see. And know that like we have basically c log c over 1 minus beta is equal to free energy, right? So let's rearrange the terms to get this thing here. So I have like log c. Oh, okay, maybe should be consistent to use ln here, but sorry for the confusion, but like lm and log is the same. So I just use two different notations here. So let me use Ln here. Ln here. So and I have Ln C over beta. So this minus beta. That's actually the definition of the free energy. Is therefore is equal to let's see, I over beta here. This move the other side, so I have Ex here minus S over beta. Yeah. And of course, like beta is inverse energy, or I can write it as like Ex minus Ts. And this is U minus Ts. This is like the so-called Helmholtz free energy in chemistry and physics. And by the way, like maybe talk a little bit more about like what this free energy actually is in physics. Like we just try to get a little bit revision. I don't know, like it's not a brief, I would say, like revision of like thermodynamics in I guess like elementary physics. So remember that like in physics, like when we study thermodynamics, elementary thermodynamics, like we have like some internal energy like U. When there's change, okay, this is the internal energy. The change of internal energy for some gas will be like have like T ds minus P dV. So where P is pressure here, V is volume. So T is the temperature, of course, and S is the entropy. So in the sense that your internal energy change when you keep the temperature, when the entropy increase. So your internal energy will increase, and at the same time, like it will decrease when we keep the pressure the same, but we kind of like decrease the volume. So it's like it wait should say, yeah, decrease the volume, the internal energy. I'm thinking why decrease the volume, internal energy should in yeah. You increase the that's right. Increase the volume, the internal energy will decrease because you're doing work, right? So then yeah. So therefore they should be opposite side. Yeah, that should be fine. Now and okay, another remark here is that like know that like what I'm writing it this way because like SMV here is actually the independent variables. Like you can independently change like SMV here in this case. And also like another remark is that like SMV here are both like extensive variable, like extensive. I should maybe write better. And P and T are intensive. Like extensive, like is in the sense if you increase the size of the system, for example, you double the size of the system, then the value will be double as well. But for intensive value, like if you intensive variable, if you double the size of the system, that value is not supposed to change. So and U is like literally kind of like described with this equation here. So and U is therefore it's actually a function of like SMV here. And it's like SMV, you can independently change that. The T and P somehow like are the variables that will be kind of like related to the remaining variable. For example, like if I change SMV here, U will change, and T will change according to this USMV here. And and so what of okay. Now back to like why we want to have free energy. Basically, I find like two reasons about that. Like I guess I guess maybe uh, at least to me it's a kind of like acceptable reasons. So first of all, like in terms of the internal energy, even though you're given the internal energy, it's not all energy there is usable, in the sense that not all of them is can do work, because you can think of like you can have like high internal energy by like keep increasing your entropy, but you know that if in a closed system, if the entropy is maximized, you cannot do any work. Uh, because like by second law, like if um, um, there's no gradient of like temperature or something, if everywhere is equilibrium, like in that sense, I will achieve like maximum entropy, then that's basically like there's no heat flow from one side to another. That's no automatical heat flow from one side to another to do any work for you. So therefore, like you can have high internal energy, but like you cannot do any work. So free energy is captured in the sense that like what is the actual amount of energy I can use. And another reason, like it's not exactly that reason, is that S is not a very usable like variable here. I shouldn't say usable, but as an independent variable, it's not easy to control the entropy. So it will be much nicer to control, for example, the temperature and the pressure instead, right? So if you want to get, but here, like actually T and S are conjugate variables, like they are conjugate to one another. So you can either select S or select T. So instead of like taking S as a independent variables, S and V as independent variables, it'll be much easier to deal with, like to use like T and V, for example. Uh, this can be easily done by using the Legendre transform. Uh, so the Legendre transform is basically just a special case of converse conjugation. Converse conjugation. Um, so it's a very simple idea because you know that like the total derivative is given by that. So if I consider like u minus ts here, what do I get? I will have like dts. I will have dt dt or sdt T ds, right? And du here, I'll have T ds and minus P dv here. So if I consider the total derivative of this thing here, I have T ds got cancelled. Now only I have this expression here. Now I call it this free energy, or like more precisely, it's actually the Helmholtz free energy. And it would be a function of VMT instead. So it's like basically a function of VMT, and it's actually equal to minus P dV. Oh no, actually I shouldn't say that. I mean dF here will be equal to minus P dV and SDT. And by the way, that's why we have this U minus TS here is known as the free energy. Basically, it's the Helmholtz free energy here. A further remark is that, like, of course, I can do Legendre transform like more. For example, like I can also do it one more time. For example, like I can instead of like having PdV, I don't want to have V as the variable. I can add, for example, like U minus TS plus PV. Then I will basically have like PdV get gone, and I will have like VdP instead. And then in that case, like we have this so-called Gibbs free energy. We'll have like P and temperature as the variables, and in terms of like kind of probabilities and Bayesian probabilities and like machine learning, it's Gibbs free energy is not very apparent how we can use that, because there's no natural definition of pressure and volume directly, like in probabilities. But entropies and temperatures naturally came across. So so therefore we have Helmholtz free energy. We have the free energy, basically it's just the Helmholtz free energy. Let's see, oh yeah, and the final remark here, the free energy, why we call free energy again, like for the Helmholtz free energy, it turns out will be the amount of energy that effectively can do work for constant volume and temperature. So yeah, so that's why people call it free energy. And in terms of Gibbs free energy, will be the amount of energy remaining can do work. Effective energy can do work under constant pressure and temperature. More precisely, should be the long PV work, in the sense that not including like changing the volume, but yeah. So, but any work, for example, like if you have like chemical energy inside, like you can do some circuit things, like let some circuit run, then the energy can be extracted to do that kind of circuit under constant pressure and temperature. The maximum energy that can be effectively extracted will be like the Gibbs free energy in that case. So okay, that's basically all I want to talk about this free energy. But let's finally maybe just go back to machine learning here. So and from machine learning, like we can think of this free energy just so if I have the Boltzman distribution, let me write the Boltzman distribution again. So maybe I have variables like x, y, z here. So my expression is a minus beta. So I have the partition function here. Or maybe I just write. Yeah, it's okay. Okay, let me write it explicitly. So I have like let's say p x y c is equal to this. Okay, let me write like this. Okay, this is like the probability for all these variables here. But let's say like if some of them are latent, so if I'm going to kind of like not going to see these variables, I'm only going to see the remaining variable. I have like pxy maybe. So my free energy there, I mean, when I think about the free energy there, I can think of like it's actually the effective energy excluding the latent variable. So I may have like f here, x and y, and then I have another partition function. This will be a different partition function, by the way, though. Because this basically will be just equal to f x y dx dy, something like that. And by the way, like maybe at the end I will just take an example from slides in from Lecun. So from a course by Lecun, here's a very nice course like on machine learning. So this is like from one of his slides, but I guess I will just write it down here. Basically, like he's thinking, okay, let's write consider like I have like x y c given x. Let's consider y c given x, and here is a from this one to y c given x, I will have this over x, right? So the partition function will get cancelled. So I should have what I mean, like this will be equal to p x y z over P x y z integrate ymc or dymdc. And so I pxyz, if I plug in here, my partition function get canceled. So I will just have like minus e minus beta exyz e minus beta exyz dx dy. Okay, something like that. Now let's say like if z turn out is a latent variables, right? If this is a latent variables, so I may try to integrate that out. So I have like p marginalize that. So py given x. So I will just say integrate z out. So this derivative this thing dc out. So what I have to basically just, so therefore like I will have something like e beta e x. Okay, I try to write a little bit better. Let's see. Beta e x y z dz, right? And yeah, that's it, right? Beta e x y z dx dy. Now, but I can think of this as e to the minus beta log this expression instead, log. And actually, I can call this maybe, yeah, I just realized I have 2z here. Okay, I'm so bad. I'm sorry about that. Yeah, I just realized that it probably is not a good idea to have like this. Yeah, it's okay. It's okay. I'm not. Yeah, yeah. So please note that I have this C earlier. I say this is the partition function, but C here is just a variable basically. Yeah, sorry about that. So so therefore like okay, let me here. I just write the whole thing then. So I can have something like this way. Let's see. E to the exponent e to the minus beta log this 1 minus beta this thing, right? So I can copy this thing. Okay, but this is basically just an inverse function of this guy, right? E to the minus beta is inverse function of log 1 minus beta multiplied by something. So these two things we got canceled. But then if I do that, like this thing here, I can just call it this f xy here basically is essentially is exactly the free energy excluding the latent variable basically, and the denominator can do the same thing. I can instead of like the, let's see, denominator I have actually here I have a mistake here. Denominator should be dy and dc here. Yeah, I made a mistake here. Dy and dc. This is a. So again, I can do the same thing. Like for this part here, I can write it as like e to the minus beta f xy instead, and then dy. So then you can see the form is like exactly the same as before. Essentially, this thing like after like, let me write it better, like e minus beta f xy e minus beta f xy dy here. So this form and this form is essentially exactly the same here. So you can just see like that instead of my energy, say x, y, and c here. Now I only have like energy, have like variable x and y. So we can think of this F really the effective energy. It's like same as before, but we just have the latent variable get marginalized, and this free energy is just given by log 1 over beta wait a sec, I want to make sure wait. Okay, I think I should be yeah, I'm sorry, like here I have another mistake. How can I do this? Yeah, that's so silly. Yeah, I'm so sorry about that. Yeah, this now can get this part is exactly inverse of this part, right? I have beta minus beta multiplied by minus 1 minus beta, I got cancelled. And exponential and log again got cancelled. So yeah, it should be like this. So therefore, like f should be equal to 1 minus 1 over beta log the partition function, basically. The partition function calculated by marginalizing all the latent variables, basically. Yeah, okay, that's it. So in conclusion, like we have in machine learning, again, like my our free energy is essentially just the effective energy, just like the normal energy, but with the latent variable get excluding out, or like get resolved somehow, and it's resolved by constructing the free energy in this way. And that free energy is related. Why it's called free energy? Because it's related to U minus Ts, basically, in thermodynamics. So okay, I'll just stop here. Thank you.